Welcome to the Deep Dive, where we crack open the densest sources and give you the essential distilled knowledge you need to be the expert in the room.
Today, we are focusing on a technical process that is, well, it's foundational to global industry, yet it really sits in the shadow of the, let's say, sexier engineering disciplines.
We're talking about solid-liquid separation, or SLS, specifically in the mining world.
Exactly.
I mean, when you look at a mine, you picture the giant trucks, the massive crushing machines, the sheer scale of it all. But so much of the high-stakes engineering happens right at the end.
It does. It's the part where you're trying to separate massive quantities of valuable mineral from, just enormous amounts of waste and water.
And our source material today, excerpts from the highly technical volume solid-liquid separation in the mining industry, is going to be our guide through that.
And our mission really is to get a handle on the fluid mechanics, the complex mathematics, and the surprisingly long history behind these core processes of thickening and filtration.
And this isn't abstract theory, is it? This is the hidden infrastructure that dictates the economic viability and, I suppose, the environmental responsibility of every major mining operation on the planet.
That's it, exactly.
So let's start with a piece of critical self-reflection from the source material itself, which I think frames the entire history of this field really well. It talks about a long-standing academic carelessness.
Academic carelessness. That's such a powerful phrase.
It is a carelessness toward solid-liquid separation, thickening, filtration, and pulp transport in engineering programs.
And it's a really powerful indictment, but, it comes from a place of clear-eyed analysis. For decades, research just naturally flowed to where the industrial pain points were most acute.
Okay, so what were those traditional pain points? Where did all the energy and money go?
Well, it flowed to the front end of the plant. You have to consider this. Roughly 80% of the total energy consumed in mineral processing goes into one thing. Comminution. That's the crushing and grinding of the ore. So if you want to optimize your costs, you tack the 80% problem first, right?
Of course. That's where the research budgets would have gone.
And they did.
So that massive energy budget dictated the focus. What was the second major focus?
Flotation. This is the separation stage, the chemical backbone where you physically separate the valuable minerals from the gangue or the waste rock.
And that has its own big cost center.
A huge one. Flotation involves high reagent costs. I mean, you're buying all these chemical inputs that change the surface properties of the particles. So high reagent cost equals high research focus. Simple as that.
And our process, dewatering, the solid-liquid separation part?
Historically, it was seen as the minor leagues. The cost per ton associated with dewatering was, relatively low compared to the staggering energy costs of comminution and those high reagent costs of flotation.
So if a process only accounted for a small slice of the operating budget, it only got a small slice of the research focus.
Precisely. And that neglect created this knowledge gap that we're really trying to close today.
But that historical calculus, it's just shattered now, hasn't it? The low cost per ton of the operation is almost irrelevant because the cost of water is no longer negligible.
That is the critical insight for you, the listener. Global water scarcity has made efficient dewatering maybe the single most important unit operation for sustainability. It's no longer about minimizing the cost of the thickener.
It's about maximizing the recovery and recycling of every single drop of water.
Exactly. To maintain operational viability, especially in arid regions, and to secure what the industry calls its social license to operate, it's become absolutely paramount.
Okay, let's unpack the whole system then to see where solid-liquid separation really fits in. We're moving into our first section, the mineral processing ecosystem and the water challenge.
And to structure this, I think it's useful to use the classic definition from Barry Wills back in 1997. He identified 4 main unit operations in a mineral processing plant, what they call the concentrator or the mill.
And these are sequential.
Completely sequential. First, you have comminution, that's the size reduction. Second is concentration, the separation part. Third is dewatering, our focus. And finally, you have pulp transport.
And the efficiency of those last two, dewatering and transport, they hinge entirely on what comes out of the first two.
100%.
So let's start at the beginning, combination, because that's what determines the particle size we're going to have to deal with later. We're talking about taking run-of-mine, rocks measured in fractions of meters, and reducing them by factors of thousands.
The scale is just astronomical, and the goal is what's called mineral liberation.
Mineral liberation.
We're trying to break that rock matrix down until the valuable mineral grains, let's say copper sulfides, are cleanly separated from the worthless gang rock that surrounds them.
And depending on the ore body, that could mean grinding particles down to, what, 100 microns? 50? Even smaller?
Oh, even smaller sometimes. And the whole processing sequence really starts with the mining itself.
The blast?
Right. The first size reduction stage is blasting. Then, once the ore is delivered to the mill, the formal comminution process begins. This starts with crushing.
And that's a dry process.
Usually a dry process, yeah.
Yeah.
It involves primary, secondary, sometimes tertiary stages. And crushers achieve relatively small reduction ratios, typically taking material down by a factor of maybe 3 to 6 times its size per stage.
So crushing handles the big rocks, gets them down to, pebble size, and then we move into the heavy energy usage, grinding.
And grinding is almost always a wet process, which means we are now dealing with a solid suspension, a slurry, which is our medium for the rest of the plant.
This is where we use the tumbling mills filled with steel rods or balls.
It is. But the industry has increasingly shifted toward using these massive semi-autogenous mills, or SAG mills.
I've seen SAG mills referenced over and over in the source as a major evolutionary step. What advantage do they give you beyond just being enormous?
Well, their key advantage is that they use the ore itself, supplemented by a small charge of steel balls, to grind the material. Semi-autogenous means it's partially self-grinding.
And economically, that must be huge.
It's a game changer. A single large SAG mill can replace the entire secondary and tertiary crushing circuits and the primary grinding stage.
Wow. So it consolidates all those steps.
It does. It significantly streamlines the flow sheet and often leads to better overall energy efficiency compared to the traditional multi-stage crushing and rod or ball milling.
So after all that immense energy expenditure of comminution, we have a fine slurry where the valuable mineral is liberated. That takes us to step 2, concentration.
Usually via froth flotation.
And flotation is the core of the separation.
It really is. It's a beautifully simple concept, actually, rooted in surface chemistry. We introduce chemical reagents, collectors, frothers, modifiers that selectively change the surface properties of the valuable minerals.
And they make them hydrophobic, or water repelling.
Exactly.
Yeah.
And once they repel water, they seek out the next available interface.
Which is an air bubble.
Which is the air bubble. Air is blown into these tanks. The hydrophobic mineral particles latch onto the bubbles. They rise to the surface of the pulp, and you skim them off as a concentrate.
And the waste material, the gangue, is hydrophilic. It loves water, so it just sinks and becomes the tailings.
That's the process in a nutshell.
Now, that brings up a critical point about the scale of the operation. You said flotation works well up to about 33 to 35% solids. So you have this huge volume of liquid involved.
And that's the moment the necessity of solid-liquid separation becomes absolutely urgent. I mean, the process is inherently water-intensive, and you're left with 2 products, both of which are high-moisture slurries that need to be stabilized.
Let's talk about those 2 products then, the concentrate and the tailings.
So the concentrate, that's your valuable product. It has to be dried to a very precise, low-moisture content.
Why is that so important?
Well, 2 reasons. First, for the next process, like smelting, where excess water just adds energy cost and complexity. But second, and this is critical, for safe transportation.
Right. The International Maritime Organization has very strict rules about transporting mineral concentrates.
They do. If the moisture content is too high, the material can undergo liquefaction during transit.
Liquefaction. That's where the material suddenly shifts from acting like a solid to acting like a liquid because of the ship's motion.
Yeah.
That's a huge safety and cargo loss risk.
It is, and it has led to catastrophic sinking events in the past. So dewatering the concentrate is an absolutely mandatory safety requirement for global trade.
Okay, so that's the concentrate side. On the other side of the ledger are the tailings, the waste rock mixed with all that processed water. This is where the water challenge really crystallizes.
The tailings present a dual challenge: environmental safety and economic recovery. Environmentally, you can't just dump this huge volume of water. It's contaminated with reagents and dissolved solids.
And economically, the water itself is a valuable, finite resource.
It is. Most of that water must be recovered and recycled back to the front of the mill.
Let's put some hard data on that. I think the case of water management in arid mining regions like Chile, which the source details, is really telling. This is where that 18-cent number becomes a huge insight.
Right. Look at the economics from about a 2010 perspective, operating in a desert environment. Purchasing fresh water costs roughly 50 cents US per cubic meter.
Which is relatively cheap, but the supply is diminishing.
It's getting tighter and tighter, and as those supplies tighten, the industry is forced to look at alternatives, primarily desalination.
Desalination, which involves massive energy costs for pumping and reverse osmosis.
And that cost was $2.20 US per cubic meter. That's over 4 times the cost of fresh water.
For a mine that might need tens of thousands of cubic meters of water a day, that cost just becomes prohibitive.
It really does. But this is where efficient thickening pays off.
Okay, so what was the cost of the recovered water?
The cost of recovered process water, that's the water pulled directly from the tailings through efficient solid-liquid separation, was only 18 cents US per cubic meter.
18 cents. That is nearly 92% cheaper than desalination.
It's an incredible difference.
If you scale that up, say a large concentrator uses, conservatively, 100,000 cubic meters of water per day. Recovering that water, instead of relying on desalination, saves the company over $200,000
Per day.
per day.
And that scaling, it just transforms dewatering from a simple cost input into a core strategic technology. It is the single most effective way to lower operating expenses, manage scarcity, and mitigate environmental risk all at the same time.
That academic carelessness of the past is it's completely unsustainable in today's water-scarce global economy.
It absolutely is.
That economic shift makes it so clear why we need to master the technical mechanics. So let's move into our second section, a deep dive into dewatering mechanics, sedimentation, and consolidation.
Right. As we've established, dewatering is accomplished by combining 2 fundamental physical processes. There's thickening, which uses gravity separation or sedimentation, and then there's filtration, which uses pressure to force the water out.
And the challenge in both is the ultra-fine nature of the particles that you need for efficient mineral liberation and concentration.
That's the whole problem.
Now, the idea of using gravity to separate solids isn't new. It's pretty intuitive. We've got evidence from the 4th Egyptian dynasty of washing gold, but the source also highlights a more formalized historical step.
Yeah, we can look at Agricola's 16th century descriptions of European copper washing at places like Noosa Hall. He detailed these settling tanks that were used in batch or semi-continuous operations.
But they didn't have pumps or continuous feed. They were just using large tubs.
Exactly. They'd introduce a slurry, the solids would settle to the bottom, probably overnight, and then the mud was manually removed, likely with a shovel. They had the practical know-how, but, zero mathematical theory.
That mathematical analysis arrives much, much later, right at the dawn of the 20th century.
It does. In 1904, a man named Hazen provided the first serious mathematical analysis of particle settling, but in dilute suspensions, a process we call clarification.
And his finding was seminal, wasn't it?
It was. For clarifying water, so removing just a small concentration of solids, he found that the efficiency is proportional to the tank surface area, not the volume or the detention time.
Why is surface area the key constraint there?
Well, because clarity is achieved when every particle has a chance to settle before the overflow leaves the tank. A wider tank provides a greater settling area, which allows particles to reach the bottom without being swept out by the flow. It doesn't really matter how deep the tank is.
And that insight fundamentally changed the design of industrial settling tanks.
And the very next year, 1905, Dorr used that knowledge to invent the continuous thickener, the machine that still defines the industry today.
It's amazing. The source shows the core components haven't really changed that much. A big cylindrical tank, a central feed well, the overflow launders around the edge for the clean water.
And the slow-moving rakes on the bottom to collect and compress the settled solid, which is then discharged as underflow. It just transitioned the whole process from a labor-intensive batch operation to a continuous, high-volume industrial process.
So after Dorr's invention, researchers like Coe and Clevenger tried to understand the physics inside that continuous system. And in 1916, they provided this foundational observation for flocculent suspensions. What were the 4 zones they identified?
If you look at a batch settling test in a transparent column, the 4 zones are really distinct. At the top, you have Zone A, that's the clear supernatant, the recovered water.
Okay. And below that?
Below that is Zone B, the zone of constant initial concentration. And this is characterized by what's called hindered settling.
Hindered settling. That means the particles aren't settling freely like in Hazen's dilute clarification model.
Right. They're so close together that they interact strongly through the fluid, they slow each other down, but they're all still moving downward at the same velocity, so they maintain a sharp interface with zone A above them.
And then zone C is the transition zone.
The transition zone where concentration starts to increase rapidly, and then finally at the very bottom you have zone D, the compression zone, where the solids are densest.
And their major takeaway from this was the concept of maximizing solid handling capacity, or solid flux.
Yeah, by understanding how quickly the solids settled at various initial concentrations, they could figure out the optimal dilution in the thickener to maximize throughput. For decades, that solid flux method was the most reliable way to design industrial thickeners.
So this macroscopic observational work was then codified mathematically by Kinch in 1952. And this is where the field really gets into rigorous fluid dynamics. What was Kinch's key theoretical breakthrough?
Kinch developed what's called the kinematic theory of sedimentation. It's based on a conservation law for solids, and he mathematically described how the settling process occurs not by the bulk fluid moving down, but by concentration waves propagating upwards.
Concentration waves propagating up. That's a difficult visualization.
It is. I mean, think of it less like a physical ocean wave and more like a shock wave of density. As the compression zone at the bottom grows, it sends a wave of higher concentration upward, and that slows the settling rate of everything above it.
And the mathematical solutions that describe this process are called hyperbolic equations.
Exactly. And to make a system like this solvable, you need a conceptual simplification, something like the ideal gas in thermodynamics.
And that's the ideal suspension.
That's the ideal suspension, defined by Shannon and Torrey in 1966. Just like an ideal gas assumes negligible volume and no intermolecular forces, the ideal suspension assumes uniform particles and that the settling velocity depends only on concentration.
Which isn't true in reality, but it gives you a baseline.
It gives engineers a rigorous, idealized baseline. And while real industrial slurries are far more complex, this model actually approximates simpler, unflocculated systems, like certain copper concentrates, surprisingly well.
Now we get to the critical demarcation line.
Yeah.
The physical difference between sedimentation and consolidation, which, as you mentioned, dictates the governing mathematics.
And this is really the crux of modern dewatering science. Sedimentation is defined by the particles settling individually. They only interact via fluid pressure and friction. They're free to move relative to one another.
And this is governed by those hyperbolic equations.
Right, which are necessary for modeling transport and wave propagation. But at the critical concentration, the compressive yield point, the physics fundamentally changes.
It does. At that concentration, the particles start to touch. They interlock, and they form a continuous self-supporting network, the sediment.
And that physical structure can now resist stress. So if the particles or flocks are compressible, which is typical for flocculated tailings, the weight of the material above them compresses this network, and it expels water from the microscopic pores. That squeezing action is consolidation.
So sedimentation is governed by transport, while consolidation is governed by compression and diffusion.
Exactly. And compression, which is governed by the diffusion of pore water through the particle network over time, requires a completely different mathematical framework. Nonlinear, degenerate, parabolic differential equations.
So that mathematical interface, the moment the system switches from hyperbolic, which is settling, to parabolic, which is squeezing, that's defined by the critical concentration.
Precisely. And modern thickener modeling has to solve both equation types simultaneously to accurately predict the final underflow density. It's incredibly complex.
It's the fine particles that necessitate this complex math. They slow the settling so much that we have to artificially speed up the process, which brings us to our third section, flocculation, thickener design, and modern instrumentation.
Right. Dealing with fine particles that are often 1 to 10 microns in size, it's just impossible without chemical intervention. The first step is what's called coagulation,
which reduces the electrostatic repulsion between particles, letting them get close to each other.
Exactly. And once they're close, we perform flocculation.
And that uses these incredibly long, water-soluble polymeric agents, flocculants, that act as bridges.
Yes, they linked dozens or hundreds of individual particles into larger agglomerates, which we call flocks, and the outcome is critical. These flocks don't just increase the settling velocity, they also create a much more porous, permeable structure for the filtration or compression stage that comes later.
The source material describes these agglomerates using a term that's both technical and a little poetic. They are fractal objects.
They are. Flocks exhibit self-similarity across different scales. So a small cluster looks structurally similar to a massive cluster. Their fractal dimension is key to understanding how they behave under shear stress and how compressible they are.
And a higher fractal dimension usually means a denser, less compressible structure, which is generally what you want.
Generally, yes.
So, given how vital these flocks are, the process of forming them must be precisely controlled. And this hinges on two factors: the flocculant dose and the shear rate applied during mixing inside the feed well.
And the feed well, that central area where the slurry is first introduced, is arguably the most critical and complex piece of hydrodynamics in the entire thickener.
Because optimal flocculation requires two very distinct mixing stages that have to happen sequentially.
That's right. First, you need a high shear rate, maybe 500 inverse seconds, for a very short duration, like only 5 seconds. This is necessary to maximize the collision frequency between the fine particles and those long flocculant macromolecules.
So you get rapid and complete absorption of the polymer onto the particle surface.
An intense, brief collision, exactly. And immediately following that, you need a transition to a low shear environment lasting for around 60 seconds.
High low shear.
This gentler mixing allows the activated particles to aggregate and bridge into the largest possible, densest flocks without being torn apart. High shear promotes absorption, low shear promotes growth.
And that sequence, high shear followed by low shear, that sounds incredibly difficult to achieve efficiently inside a standard feed well that's processing tens of thousands of gallons of slurry per minute.
It's the ultimate design challenge. Manufacturers like Autotech have developed really sophisticated designs, like the vane feed well, which tries to provide enhanced high-shear mixing upon entry, and then a transition to a gentler, more laminar flow in the lower section to maximize aggregate growth.
And we have concrete industrial evidence showing just how critical this optimization is, don't we?
We do. Consider the examples cited in Australian mineral plants, where a simple operational change, just relocating the flocculant addition point to the lower part of the feed well to use the natural dilution that occurs there, was enough to almost double the overall thickening capacity.
Double the capacity from a small operational tweak like that.
It just underscores the sensitivity of the entire process to the point of flock formation.
But the underlying technical challenge is still there. The perfect sequence of high to low shear can't always be achieved by gravity and tank geometry alone.
And this leads us to the ultimate structural limitation. The source specifically points out that the next great technological leap in this field, the ideal solution, is the development of a specialized industrial-scale flocculation reactor located before the thickener feed.
A dedicated unit that would optimize flocculation kinetics under controlled conditions.
And deliver a perfectly conditioned feed to the thickener, maximizing its efficiency. Essentially, a unit operation dedicated solely to making perfect mud, freeing the thickener to do only the separation and compression work it was designed for.
And that specialized industrial reactor is currently the holy grail that hasn't yet been widely implemented in copper concentrators.
Not yet, no.
So let's classify the final thickener equipment itself. We go from conventional to the extreme, based on the required underflow density.
We can start with the conventional thickener. This is your classic door design, with the feed well in the upper part, where the feed slurry gets substantially diluted when it enters.
And next up is the high-rate thickener.
High-rate thickeners are all about throughput. They achieve high tonnage, high capacity through two key things: optimized flocculation and very careful control of the feed slurry concentration. They're often smaller for their given capacity compared to conventional units.
Then we move into the designs that are focused on getting a high solids content in the underflow.
That's the high-density thickener. The goal here is an underflow with a high solids concentration, maximizing water recovery. They use longer feed wells to deliver the feed directly into the top of the sediment bed, bypassing the traditional settling zone.
And they have steeper cones and taller tanks.
Right, to exert greater hydrostatic pressure on the sediment, and often they have internal structures like picket fences to disrupt the channels of water trying to escape and promote uniform compression.
And the final type, which is necessary for minimizing waste volume and building safe tailing storage, is the paste thickener.
Paste thickeners are the most extreme version. They're much taller and generally slimmer than high-density units. And that height is essential because it provides the immense pressure you need to squeeze out the final percentage of water.
And you get an underflow so dense it behaves as a non-Newtonian fluid of paste.
Exactly. This material is structurally stable, it's safer for disposal, and crucially, it minimizes the volume of the tailings impoundment.
Now, to manage and optimize these complex processes, you need precise feedback. And this takes us to instrumentation. We're finally moving away from what the source calls the obsolete Marcy balance.
Oh, the Marcy balance. Used for pulp density measurement for 100 years, it was essentially a bucket on a scale. It was slow, it lacked precision. The field is now fully digital and capable of real-time, in-situ measurement.
So what are the modern replacements for measuring pulp density?
Tools like the density test and the industrial pyknometer. They maintain the physical principles of the Marcy balance, but they incorporate highly precise digital strain gauges.
And this allows for immediate, high-precision results that can be expressed not just as mass density, but as the far more useful parameters for engineers: volume fraction and dilution.
That's the key.
And how do we determine the critical settling parameters, the velocities you need for design, without sitting and watching a batch test for hours on end?
That's the role of the SediRack. It's a lab instrument that performs up to 5 simultaneous settling tests. And crucially, it uses video capture and automatic data processing to instantly track the clear water interface and calculate the settling velocity curve.
So it eliminates human error and vastly speeds up the process.
It does. And that lab capability is then translated into the plant environment with the SediRack Online, or PSE.
So this lets operators take a sample from the feed well,
Determine the current settling velocity, assess the effective dilution, and confirm the optimal flocculant dose in about 10 minutes. This real-time predictive capability is just transformative for control strategies.
It lets operators preemptively adjust the feed to avoid capacity issues.
Before they happen.
And for the consolidation phase, the squeezing, how do you measure the compressibility inside the thickener itself?
That's where the SediTest Online, or SMC, comes in. It determines the effective solid stress, the compressibility of that sediment network, by measuring the concentration profile inside the thickener. It does this using differential pressure measurements at various depths.
So by knowing the solid volume fraction profile in real time, operators can precisely regulate the rake movement and the underflow pump speed to maintain the desired paste consistency.
Maximizing compression without causing blockages. This shift to digital in-situ analysis is really the bedrock of modern high-efficiency dewatering.
Okay, so once we have that perfectly dewatered concentrate or that dense tailings paste, we have to move it. This leads us to our final section: suspension, transport, and rheology in the final stages.
Transport is the vital link between all these unit operations. In a processing plant, dry ore moves on conveyor belts, but as soon as the material is wet, it travels as pulp through pipelines.
And pipelines are favored because they offer incredible flexibility, right?
Right.
They can handle complex topography easily and move massive volumes over long distances.
Exactly, like pumping tailings far away from the plant. But to design these pipelines, you have to understand rheology, the study of deformation and flow.
Because everything we're moving is a suspension, its behavior in flow is highly complex and unpredictable if you don't account for particle interaction.
That's right. And the first distinction we have to make is based on the interaction between the solid particles and the liquid medium under gravity. We classify slurries into 2 major groups.
First, you have the heterogeneous suspensions.
These are the settling slurries. They generally occur when the solid concentration is low or when the particles are relatively large, typically anything larger than about 50 micrometers.
And in a horizontal pipe, gravity is stronger than the turbulent mixing forces, so the particles segregate and settle.
They do. They create a vertical concentration gradient. And in a worst-case scenario, they form a stationary or moving bed at the bottom of the pipe, which is a disaster.
And the other side of that coin, the homogeneous suspensions.
These are the non-settling slurries. They occur when particles are very small or when the concentration is high enough that particle interaction is sufficient to overcome the effect of gravity. The entire suspension behaves like a single-phase fluid.
But with potentially non-Newtonian characteristics.
Yes. And that non-Newtonian behavior is critical for handling the concentrated pulps, like the material coming out of our high-density or paste thickeners.
So fluids that are not Newtonian don't follow that simple rule that shear stress is proportional to shear rate.
Correct. We see several key non-Newtonian behaviors. The first and most common is shear thinning or pseudoplastic behavior.
This is where viscosity decreases as the shear rate increases.
Like ketchup, it sits stubbornly in the bottle until you shake it or hit it, applying high shear stress, and then it flows easily. Many concentrated mineral pulps exhibit this behavior.
And then there's the counterintuitive behavior, dilatant behavior, or shear thickening.
Right. This is found in highly concentrated suspensions, often above 50% solids by volume. Here, the viscosity increases with an increased shear rate.
The classic analogy is mixing cornstarch and water. When you stir it slowly, it flows easily. When you punch it, it suddenly hardens.
Exactly. And in a pipeline, what happens is, at high concentrations, the particles are closely packed, lubricated by water. When you apply rapid shear, the particles are forced into a configuration that requires more space than is available.
So they effectively lose their lubrication.
They do. And you get particle friction and drag, which dramatically increases the viscosity and can lead to a pipe blockage if the pump can't handle that sudden stress increase.
And finally, for materials like dense tailings, which have a definite structure, we have to consider yield stress.
Yield stress is the minimum stress required for a fluid to start flowing. So materials like those modeled by Bingham or Herschel-Bulkley require this yield stress to be overcome before motion begins.
So if your pump pressure is below the yield stress of the paste, it'll just sit there, solidified.
And that's essential for safe tailings disposal. You want the material to flow into the impoundment, but then stop and solidify immediately afterward.
Now, for designing pipelines carrying those heterogeneous settling slurries, where the particles are large, the single most important parameter has to be the transport speed.
It is. You are constrained by the limiting deposit velocity, or LDV. This is the absolute minimum velocity required to ensure that particles do not settle and form a stationary bed at the bottom of the pipe.
If you drop below the LDV, you risk a catastrophic blockage.
You do. And the consequence of this constraint is massive. It forces engineers to design the pipe system to run significantly faster than they would if they were just pumping pure water. And this high operating velocity translates directly into very high power consumption and immense energy costs just to keep the solids suspended.
Is there a universal equation to determine this crucial LDV?
Unfortunately, no. Because the physics of turbulent suspension is so incredibly complex, engineers are still reliant on empirical relationships, like the well-known Durand and Condolio's equations, which are derived from vast amounts of experimental data.
So that lack of a perfect first principles model adds complexity and conservatism to the design.
It does.
When we calculate the pressure drop in these pipelines, we rely on the Reynolds number to determine if the flow is laminar or turbulent. But pipe roughness is also a huge factor.
A huge factor. And Nicorodzy's classic experiments on rough tubes provided the essential visualization here. He showed that the resistance to flow depends critically on the height of the roughness protuberances relative to the thickness of the laminar sublayer.
The laminar sublayer being that thin, slow-moving film of fluid right next to the pipe wall.
Yes, so if the pipe roughness is smaller than that laminar sublayer thickness, the pipe acts hydrodynamically smooth, and the roughness has very little impact on the friction factor.
But as the flow speeds up or the roughness increases, the protuberances poke through the sublayer.
And once they puce that sublayer, they generate vortices and massive drag, which drastically increases the friction factor and, consequently, the pumping energy required.
That means even tiny imperfections in a pipe designed for turbulent flow can have a measurable impact on the energy budget. It connects the microscopic state of the pipe wall to the macroscopic energy consumption of the entire plant.
Absolutely. And just to finish on transport, outside of pipelines, the industry also uses open channels for bulk transport, primarily for flotation tailings disposal.
Right, the source shows images of these massive channels carving through the landscape. How is the flow classified there?
Well, open channel flow is first categorized by depth so, uniform or non-uniform, but hydrodynamically, we classify it based on its speed relative to a surface wave using the Froude number.
Subcritical flow and supercritical flow.
Exactly. Subcritical is when the flow velocity is less than the surface wave speed, and supercritical is when it's greater. But for transporting non-homogeneous slurries in those channels, the key thing is turbulence.
You have to keep it turbulent.
The flow must be maintained in a turbulent state regardless of whether it's subcritical or supercritical. That turbulence provides the necessary mixing energy to keep those larger particles in suspension until they reach their final destination.
This has been an essential journey. I mean, taking us from the strategic economic necessity of water recovery right down to the precise particle mechanics of flow.
The evolution of solid-liquid separation has been really remarkable. It started with simple ancient gravity washing, and now it relies on a deep synthesis of fluid mechanics, particle technology, and continuum mechanics, specifically the rigorous framework of the theory of mixtures to govern the design of all this modern equipment.
And the driving force wasn't academic curiosity, was it? It was a strategic imperative. The necessity to recover water forced the industry to invest heavily, overcoming that decades-long engineering blind spot.
Completely. Dewatering is no longer some downstream cleanup operation. It's a core strategic process that dictates profitability and sustainability.
And the capacity jumps achieved through feed well optimization, coupled with the precision offered by new digital tools like the SediRack Online and the Seditest SMC, they demonstrate the current state of the art.
They really do. They show how we're optimizing sedimentation and consolidation right now.
But we discussed that the current limitation is the inability to perfectly achieve that necessary high shear, then low shear flocculation sequence within the thickener feed well.
Which brings us back to the final provocative thought for you to explore. If the pursuit of maximum water recovery and optimal thickening capacity demands an industrial scale, specialized flocculation reactor placed upstream of the thickener, a unit operation that does not currently exist in the standard flow sheet.
How will this necessity fundamentally reshape the layout, the design, and the cost structure of the next generation of mineral processing plants?
Will the plant of the future be defined by its flocculation reactor? That's where the deep engineering continues.
Thank you for guiding us through this critical yet so often overlooked corner of global industry.
It was my pleasure.
And thank you for joining us for the deep dive. We'll see you next time.